Sorry. Okay. I think we're in good shape here. Okay. So I plan to continue where we left off last time, yesterday. So I'm going to, mostly I focused the time available in my last presentation on magnetic superspace, and also talked a bit about representation theory or symmetry mode analysis. Today I'm actually going to introduce the tools of the isotropy software suite and show how they can be used for magnetic structures, to build magnetic structure models, to compare magnetic structures, and to export structures for refinement in packages like FullProf or Topaz or GSAS. So the isotropy software suite came into being in approximately 1995. I was actually a graduate student at that time, and I was not involved. I was a young kid. My colleagues at BYU, Harold Stokes and Dorian Hatch, originally created the software suite. The original tool was isotropy. So this is the one that was placed online in 1995. And then I got involved about 10 years later in approximately 2005. I remember I did a postdoctoral fellowship at Argonne National Laboratory in the US, and I showed up for work, as a postdoc in November, I think November of 1999. And I think my very first day at Argonne, there was a special guest lecturer, Juan Rodriguez Carvajal. My memory could be wrong, but I think it was my first day at Argonne, and you were there. And I sat next to Juan at lunch, and I told him that I was struggling with very complex structural problems, and that I wished it was possible to only break part of the symmetry and not like break everything and have so many new free parameters. And Juan kind of smiles, this smile. He said, "I'm working on that." But he didn't tell me anymore. And then I think a few months later, he released BASI-REPS. So this, after completing the postdoc, I moved to BYU as a faculty member, Brigham Young University, and began working with Harold Stokes and Dorian Hatch. And that's kind of how I got involved. But the group representation theory is a very powerful tool for building models and controlling the degree of symmetry breaking that you want to allow in your system. When you break the symmetry in principle, a lot of new parameters come into existence that are difficult to deal with. But when you're using the representational analysis or symmetry mode basis, you can simply turn off all of the parameters you don't want to deal with by fixing them at zero. It's a very nice approach. So, many of these tools in the isotropy software suite are relevant to magnetic structures. I'll talk about a few of them. I've been involved in the development of most of these tools, but not all of them. S-modes, FrozeSL, Copal, and ComSubs all predate my involvement, but I've worked on most of them. If you ask me a question about FrozeSL, I'll just refer you to my colleague Harold, because I don't know. I don't use that tool. So the ISODISTORT package is the main package of the isotropy software suite currently. We have not changed the original isotropy tool for many years now. It's a static tool. Most people use ISODISTORT, but there are still some people who enjoy the command line experience of using the original isotropy tool. It still works. So with ISODISTORT, you need a parent structure. You need a high symmetry structure. Remember that when you're doing representational analysis, fundamentally you're comparing two different structures. When you provide a traditional description of a crystal structure. You give the positions of the atoms in the unit cell and their local properties, like magnetic moments and occupancies, thermal ellipsoids. That's a standalone description. But when you do representational analysis, you're comparing two structures. You're presenting the low symmetry child structure in terms of the parent structure. You're explaining how the child structure is different from the parent. That is fundamentally what a symmetry mode description gives you. It's a comparison. So you have to have a parent structure. ISODISTORT, and the goal, the vision, is that it should be able to treat any combination of order parameters. You could simultaneously do displacements, magnetism, order disorder, polyhedral rotations, lattice strain, and that each of these distortions in principle can have different k-vectors, some of them commensurate, some of them incommensurate. We've made a lot of progress towards that goal. There might be a few little things that we're still working on, but mostly we have achieved that goal. But currently, the main limitation on the isotropy suite, or the ISODISTORT package, is that the parent has to be commensurate and non-magnetic, or not truly non-magnetic, paramagnetic, a gray group. So we currently can't start with a magnetic structure as the parent, or start with a superspace, with an incommensurate structure as the parent. To my knowledge, no one has ever determined the irreducible representations of the magnetic space groups, or superspace groups, or magnetic superspace groups. So without these representations, you can't really use such structures as parents. But maybe in the future, someone will do this, and it will be possible. So ISO subgroup, I think, is a tool that was motivated by an idea provided by Professor Perez Mato. He said, I want to be able to look at the subgroups, the symmetry breaking, without having a specific parent structure, to just start with a symmetry group and see what child subgroups can result. And so we now have a tool that does this, and I use it very frequently. I think maybe I use it more than anyone else, but I really like this tool. FineSim is a very powerful package for determining the symmetry of a structure from scratch. If you upload a structure into FineSim and you provide the symmetry group with the structure, the very first thing that FineSim does is it eliminates the symmetry that you provided, and then it rediscovers it again, in addition to any other symmetries that were present that you might not have been aware of. FineSim has adjustable tolerances, and so you can also detect pseudosymmetry. And so sometimes I use pseudo and FineSim together. Pseudo is in the Bilbao package, or the Bilbao Crystallographic server. It's another nice tool for studying pseudosymmetry. So at present, you can upload a commensurate structure, an incommensurate structure, magnetic or non-magnetic, and it will detect the true symmetry group. You can also take large models, like from a reverse Monte Carlo run, where you have a big box model, and it will detect the translations in the big box model and find the translational, the lattice of translations, and then complete the symmetry detection. After it detects the true symmetry, it enforces it, and then you can export the symmetrized structure. ISOSIF is a tool that was created as a support for ISODISTORT for preparing input files. You can also use it generally to manipulate commensurate and incommensurate structures, change the setting, remove the magnetic moment, strip away the incommensurate modulations if you want to. And it's got, actually FineSim, all the capabilities of FineSim are built into ISOSIF. And so you can essentially use FineSim within ISOSIF if you want to. So ISOMAG, this is just a a readable database of symmetry operations and Wyckoff site information for both, for each of the commensurate, for each of the commensurate magnetic space groups. There are 1,651 of them. It's kind of an old resource. It's been around for a long time now. We originally completed it, I think, in 2008, and a lot of people have used it since then. But I think most people have taken the database and incorporated it and don't actually refer to this website anymore. Let's see, the ISOIR database. So this is the only complete tabulation of complete space group erupts, not little k erupts, but complete space group erupts for all of the special and non-special k vectors of all crystallographic space groups. So it includes both commensurate and incommensurate k points. I think, I don't know if the isotropy software suite will still exist in 30 years, but I'm sure this database, ISOIR, will still exist and be useful then. The ISO 3+D dimensional website is a tabulation of superspace groups and also magnetic superspace groups now. It has all of the group operations, Wyckoff site information, k vectors, and so on. So that includes data that you can browse and also things that you can download. The ISO space group tool is a little bit newer. It's just a tool for exploring the symmetry operations, in a user-friendly and convenient way for each of these commensurate and incommensurate magnetic and non-magnetic groups. Find SSG. This is a tool where you can take a list of operators. It's often the case when you work on a incommensurate magnetic structure that you get a list of operators, maybe from Jana, and you wonder what is the group for these operators. You can copy the operators and paste them into Find SSG to find the answer. And then Transform SSG is a tool for manipulating the settings of superspace groups and magnetic space groups, starting from any reference point. So ISODISTORT, I think I checked a couple of months ago to see how many people were using ISODISTORT, and I think in a 2-week period, I saw about 12,000 jobs, 12,000, server accesses. I think roughly 30% of the accesses were from North America and England. Another 30% were from the rest of Europe, and approximately 40% of the accesses were from China. So I guess there must be a lot of people here using the package. ISODISTORT has, after you upload the parent structure, there are 4 different types of searches. Maybe what I'll do at this point is just kind of move on to some demonstrations. I'll demonstrate some of the tools for you. You don't need to follow along. After lunch, we're going to have a hands-on tutorial where you work through the exercises yourself. So I'll maybe just give you a bit of a tour here. So this is the Isotropy Software Suite homepage. And maybe the first thing I'll do is explore ISOSIF. So we can use ISOSIF to build a structural model. If you were looking for a really advanced tutorial, this is going to be really basic. I apologize. So, those of you who are experts, maybe you can help some of the others. Okay, so let's create a new SIF file. We choose a symmetry group, so we go down and maybe maybe do a cubic perovskite. So you can enter 221 here, or if you like, you can simply type 221 and it will find it for you. Or you can type the number into the box over here. You can also do that. I forget which one overrides the other if you do both. Because this is a cubic group, we need to specify the A lattice parameter, maybe 3.94 angstroms. If a parameter isn't free, you don't need to specify it. You only need to specify the unique parameters. And so, so we put in 3.94. I think a cubic perovskite has 3 unique atoms in the unit cell. So I'll just hit go. There are a variety of space group preferences. You know, ideally, I admit it, this is a weakness, but ideally you would wait until after you completed the analysis to choose the space group setting. But because of the way the code was developed over the years, it's actually necessary to specify those preferences at the beginning. Usually, normally you just choose the defaults. So, you know what I think I might do? I think maybe there are a number of people that are also using the server right now. For my own convenience, I'm going to open a local server and use that instead. That way my tutorials will be a little faster, but I just need a minute to start up the VM. So with ISOSIF, you can build models, you can also change settings, you can strip away magnetic moments from a magnetic structure or add them back in again. Yeah, here we go. Okay. I think this will be more convenient for me. Let's try using that server instead. Here we go. Thank you for your patience. Okay, so we'll again do 221, 3.94, maybe 3 atomic positions. And we'll call the first one lanthanum. We'll put that at the center of the unit cell. Maybe make the next one manganese. We'll put that at the origin. And then put in an oxygen atom at 0.500, right there. And then, you know, you can visualize the result. There's a tool called ISOVIS. I encourage you to install it before the afternoon tutorial. If you do that, you can visualize the structure. You can see we have a cubic perovskite. It's possible to change the setting. You know, if you prefer putting the lanthanum at the origin, some people like the A site at the origin, you can do a setting transformation. And then in this new setting, you're going to see a nice octahedron in the center. So you can do setting transformations. The only limitation on the setting transforms is that they cannot change the form of the operators. We can drop the symmetry to P1. Currently, we only have 3 unique atoms. You can see lanthanum, manganese, and oxygen. If you reduce the symmetry to P1, you'll see now we have a lot of free parameters. If you open the CIF file, you can see you know, you have 3 independent oxygens now. And if you click on Detect Higher Symmetry, this essentially runs the FindSim routine behind the scenes and detects the symmetry and raises it back up to the level of space group 221. You can also export files to CIF using alternative settings. For example, if I double the unit cell in each direction and open the CIF file, you're going to have a lot of operators. Instead of, you know, let's see, how many operators do we have? 384. So 48 times 8. But we still only have 3 unique atoms. And so you can use non-standard settings when you export a CIF file. And I know those of you who work on magnetic structures really love alternative settings. The chemists who do non-magnetic structures, they never ask me for non-standard settings, but the physicists especially who do magnetic structures really like this feature. So this was also inspired by Juan and Manu, who pressed me for this feature. It's quite, I think it's quite useful. Let's see. Okay, so another thing that you can do with ISOSIF, I'll just start over here. You can import an existing magnetic structure. in the tutorial files, I have these input files. I'll bring in a distorted, a displaceively and magnetically distorted lanthanum manganite. We'll take a quick look at the result. So let's imagine that we downloaded it from the Bilbao Crystallographic server. We could, there are thousands of structures there to download. So here you can see we have, for this cubic perovskite, we have a magnetically ordered manganese site where you have alternating ferromagnetic layers. So globally it's anti-ferromagnetic, but the individual layers are ferromagnetic, so it's an A-type structure. And if you want to do a symmetry mode analysis, do representational analysis, you need a parent structure. It's actually quite easy to create your parent. Maybe the first thing we'll do is we'll just remove the magnetic moments. That changes the symmetry. Now, instead of having a magnetic space group, we have an ordinary crystallographic space group. If we look at the result, you can see the moments are gone. But the structure is still fairly distorted. You have octahedral rotations. But we can also eliminate those by detecting pseudosymmetry. So I'm just going to maybe increase the lattice strain tolerance. I'll make it way too big. 25% is way too big. I only need it to be big enough, right? But I don't know how big is big enough, so I just guess. Maybe 25%. And I'll try 0.5 angstrom displacements and try detecting a higher symmetry. So I allow some tolerance, allow the atoms to move a little bit. And I didn't find a new symmetry group, so I'll go back. Maybe I'll raise this to 0.75. Still no higher symmetry. So maybe we'll do, let's see, maybe 1 angstrom. If we try 1 angstrom tolerance on the positions. Now I get a warning. It says, I've gone too far. The nearest neighbor distance between atoms of the same type is 2.7 angstroms. And they only allow 33% of this distance, so that my maximum tolerance is 0.9. But there's a secret. It's an unpublished secret. I'll show it to you. We'll go back and we'll put a second number in here. 0.33. That's the max, that's the limit. 33%. I'm going to increase it to maybe 50%. We'll just make it a little bit bigger. And now the warning is gone, but the symmetry is still the same. So I failed again. So now I'm going to, I went too far. Here we go. So now I'm going to increase this to maybe 75%, and I'll increase this tolerance to 1.25. And now I have success, cubic. So I've eliminated all of the distortions. I started with a distorted magnetic structure, and I created a parent structure, a high symmetry parent. Now I could have used the space group 62 as the parent. That's no problem, and I could have compared the non-magnetic to the magnetic structure with the same displacements. But if I want to simultaneously explore the displacive distortion and the magnetic distortion, it's possible to eliminate all of these distortions, and I get a nice cubic parent, and I can export that. I can save that. So you download any structure from the Bilbao Crystallographic server, or take any structure from the literature, and then you can create a parent structure from it, and then do a comparison of parent versus child. So maybe I'll do that now. So I've already saved the files previously, and so I think I'll just open the ISODISTORT package here, and we'll browse for a parent structure. So I'm going to use that cubic lanthanum manganite as the parent. I hit OK. And I have to choose. Juan showed this very nicely in his talk, so I'm being a little bit repetitive. I apologize. I really appreciated those examples, by the way. So you have to choose what kind of order parameters you want to examine. I think I'm going to keep the displacements because they interest me at the moment. and I'll also let manganese be magnetic. And I have to hit the change button. It's really important to do that. You notice these menus down here, they're all non-magnetic menus. They only have non-magnetic groups in them. And so when I hit change, it rewrites the entire page and changes all of the menus to adapt to your choices. So if you don't click that, that's the most common mistake people make, including me. I sometimes forget to click it. And then down at the bottom, you also have the opportunity to specify some space group preferences if you have them. I'm just going to use the defaults right now. But there are a couple of things that we can do. The method one, there are 4 different methods for comparing, for creating a child structure. The first one is very limited. This allows you to use a single irrep at a special K point, like 0.5, 0.0 or 0, 0.5. You're not going to be able to do 1/3, 1/4, 1/8 with this database here. This is a filtered search over a table of approximately 15,000 simple cases. Now, your magnetic structure may well be one of those simple cases, and so you can, for example, you can say, I want to see all of the trigonal entries in the table that are subgroups of this space group 221, and it will show you all the trigonal options. So there's just a handful of them. Each one of those is going to be a completely different distortion with different degrees of freedom, a different magnetic structure. I could alternatively, you could say, show me everything that has this conventional basis. And it will give me a list of all of them. In this case, there's just one. Maybe I'll open it, just because I'm curious. This is the main page in ISODISTORT. When you arrive at this page, all of the group theory, all of the difficult analysis is done. From this point, it's all user output and convenience. So this particular isotropy subgroup, this child, results in magnetic space group R3 bar C dot 1 prime underscore C. So let's just take a look at the degrees of freedom. I did this randomly. I also don't know what we'll find. Random exploration. So it looks like a rhombohedral unit cell with an antiferromagnetic structure. There you go. So apparently, if you enter a cubic perovskite and ask for this particular basis, this is the only distortion, the only magnetic structure with that particular basis. So I'll go back. So this, again, we were exploring method 1 here. It's a filtered search. You can filter for maximal subgroups, for example. I don't use method 1 very often myself. Yes? Eliminate most of the possibilities, allow you to focus on the options really interesting. But if you have no idea, you don't know your basis. Is that what you mean? Oh, maybe. Have a basis. That is basis. Have the perspective. Then you apply your units. Maybe not the conventional one. Right. Yeah. So you. Yeah, this feature is fairly limited. It is what it is. Okay. Method 2. This is a very general and powerful method. Maybe I'll do it last. Let's do something a little simpler. If you're an experimentalist and you've indexed your peaks, let's say commensurate peaks, and you have some idea of either the parent space group or the parent point group. You have some kind of information. You can limit the possibilities by specifying these things. So let's imagine, I happen to know that for lanthanum manganite, we have a root 2 by root 2 by 2 supercell. So I'll put in the basis 1, 1 bar 0, 1, 1, 0, and 0, 0, 2. And let's just filter the possibilities. Let's find all of the possible magnetic structures that are limited by those choices. And you'll see that there's actually quite a few of them. Might surprise you. So you can see there, almost 30 choices for that particular basis and that particular space group. I happen to know for lanthanum manganite that this is the one that I'm interested in. You could, of course, explore each of them one at a time, as we sometimes have to do. If you don't know the answer, you can simply build a model and export a PCR file or a CIF file, and test that model. But let's just look at the correct model for a moment. Look at the kind of degrees of freedom that are available. So here, remember we have an A-type magnetic structure. This, we find here that it belongs to magnetic ERAP X5+. The X point is half 0, 0 in reciprocal space. So you can see that the magnetic order doubles the unit cell along the long axis. You've also got some other degrees of freedom. R4+ is an octahedral tilt. R5+ is a scissor motion. That tends not to be very active in the structure. If you look down from the top, M2+ is a Jahn-Teller stretch. So due to some orbital ordering. And M3+ is a very common mode. It's a checkerboard rotation in the plane. You also have some lattice strains. So once you identify a child structure, it's going to have certain degrees of freedom available. If you choose a different one, you'll have different degrees of freedom. So let me go back here to one of the other possibilities. Maybe I choose the next one. And let's just take a look at what it does. Actually, the two are really quite similar. They have essentially the same basis. It's oriented a little bit differently, but that's superficial. The difference is the origin shift. So you have the same space, the same magnetic space group, the same basis, but different origin shift relative to the parent. Okay, let's see. There we go. Let's take a look at this one and see maybe how it's different from the other. Here we go. Open ISOVIS. So in this case, it looks like we still have, sorry, I have two of them open now. I don't know which one is which. I should have paid closer attention. So this one still has the octahedral tilt. Actually, I have confused myself. I apologize. I could swear I clicked a different button that time. So it's this one versus this one here. Let me try that again. There we go. So this one has I see. So it has some similarities to the original model. It also has the Jahn-Teller stretch. It also has the M3+ checkerboard rotation, but it lacks the magnetic structure options that we saw before. So it provides a ferromagnetic structure, and it doesn't have the R4+ octahedral tilts. And so you can see if you choose two different isotropy subgroups, two different child symmetry groups, you end up getting very different parameters in your model. And I'll just emphasize, I'm sorry for being repetitive, but I'll emphasize These have the same space group type and the same basis, but they're different symmetry groups. Because when you break symmetry, you have to, you take the parent and you start removing operations, right? That's what symmetry breaking does. It eliminates operations. And when you have two different isotropy subgroups with different origin shifts, you may get the same space group type in the end, but the operators that you removed were different. You removed them from different places when you have a different origin shift. So same space group type, it's in the same category of magnetic space group, but the actual symmetry group is different. So origin shift matters. That's a subtlety that I think people often fail to appreciate, but it's quite an important one. So they look like the same symmetry group, but they're not because the operators were removed from different locations. Okay, let's see. Don't want to confuse myself too badly here. Let me make sure I'm going back to the, let's back up from here. No, one more thing. So let's try something here. There are a variety of different output options that you can explore. In addition to the interactive distortion, there's also interactive diffraction, which is quite a popular tool. So you can take, for the same structure, you can take these degrees of freedom and see how they impact the diffraction pattern. So here the magnetic order doesn't do anything because I'm doing X-ray scattering, but if I switch to neutrons, and I think I have to take I'll look at the powder diffraction. It's easier to see. You have to choose the right plane. You can see you have superlattice intensities rising up when you turn the magnetic structure on. For the other magnetic degrees of freedom, which are not active in this structure in reality, physically, they produce different patterns. You can also look at lattice strains and see peak splitting. This tool has some bugs, and we're currently rewriting and replacing it with a new version based on JavaScript. Maybe within the next few months, maybe early next year, we'll have a replacement for this tool. So if you find some bugs, I already know about them. Don't worry. Let's see, SIF output. Well, there's a couple of different kinds of output. Maybe we'll look at each of them. So modes details. Yeah, let's look at the primary order parameters next. So Dimitri talked about primary and secondary order parameters. For this particular isotropy subgroup, this child space group, we have a variety of different order parameters that are allowed to contribute to the structure. Some of them are magnetic, most of them are non-magnetic. You might ask yourself, which of these order parameters can take the symmetry by themselves all the way from the parent space group all the way down to the child? It turns out in this case that none of them can do it by themselves. It takes at least 3 of these order parameters acting simultaneously to go all the way from space group 221 all the way down to the child. And so you have a number of combinations. Any of these combinations can do the job. But you might wonder, which ones are actually primary? I mean, sometimes it's kind of hard to say. I'll continue to explore that question again in a few minutes. In the observed structure, in the physical structure, R4 plus has a very big amplitude. So I think it's safe to say that that one's included. M5 plus, this is the active magnetic IREP, and so we know we're going to need that one. And M3 plus, the checkerboard rotation, and also M2 plus, the on-teller stretch, are both quite big. I think this combination right here is likely to do the job. So remember that, R4 plus, M3 plus, and magnetic X5 plus. So I will now go all the way back, and we're going to try method 2. So with method 2, you can explore any IREP you like. You can choose a K point, you can pick an IREP, and you can see what it does. In this case, I'm going to go a little crazy, and I'm actually going to superpose 3 IREPs. You know, going all the way from space group 221 down to the child is, physically, it doesn't happen all at once. There's a series of multiple phase transitions that you go through in order to get all the way down to the low symmetry. But we're going to apply all of the parameters at once, it's not hard to do. So I think we're going to need an R point IREP. That's a K vector half, half, half in reciprocal space. We're going to need an M IREP and also an X IREP. So I've chosen those 3 K vectors. It's going to be a multi-K experience. I'm going to choose IREP R4 plus, M3 plus, and maybe magnetic X5 plus. And once again, we arrive at some possibilities. It turns out there are quite a few different ways, you know, for a magnetic calculation of a cubic group. The calculation's a little bit demanding, and so we have to wait a minute, give it a second. If all of you try to do this at once, I don't know what the server will do. That's why we're going to work in teams after lunch. So let's see, here we go. We've got quite a few different options. I remember 62.448. I remember that was the correct magnetic structure. Of course, if you don't know the magnetic structure, you have some options you have to test experimentally. But I'm using the fact that I know the answer to show you how to use the software. So let's just make sure we got to the correct isotropy subgroup. So we'll look at the parameters available. Yes, there's the octahedral distortion. Here is the Jan-Teller stretch. Here's the checkerboard rotation. I think it appears that we've arrived at the correct isotropy subgroup. So in principle, we could export that model to CIF and refine it in full prof, for example. So this is another way to arrive at the same point. This is the distortion page, the main page, the results page in ISODISTORT. Now, if I want to save this result and come back to it later, I can save this file. I think I'll do that right now, just for fun. And I will call it, let me go to the workshop page. I'm just going to call it distortion.txt. Doesn't matter what I call it. And I can go back to the original ISODISTORT and or the ISODISTORT homepage, and oh, no, not that button. Down at the bottom, I can import a distortion file. So instead of making all of the choices myself, I can go back and there it is, distortion.txt, and recover a previous analysis. So it brings me right back to the same page where I have all the details. So you can save a distortion and come back to it later. I think that's a useful output form. Yes?
Of the list, because it seems quite chaotic.
That's a good question. Yeah, let me, so I'm going to make the list a little bit smaller here so I can fit all the lines. You know, it's somewhat arbitrary, but not completely arbitrary. It tends to go in order of increasing complexity. So, for example, the order parameter direction, let's look at that. I'm really glad you asked that question. So here you have A00. This is for the first IREP. This is R4 plus. This is the order parameter direction of the R4 plus IREP. B00 is the direction of the M3 plus, and then 0000CC is a special direction for the IREP X5 plus. When you see the vertical bars, that means that it's separating the degrees of freedom from the different IREPs. When you see semicolons within one of the order parameter directions, they separate arms of the star of K. And so, for example, for a cubic group, the x point is half 0, 0 in reciprocal space. That's equivalent to 0, half 0, or 0, 0, half. And so these three sections here correspond to half 0, 0, 0, half 0, and 0, 0, half in reciprocal space. There's a lot that I could say about that, actually. So here is a different example. A different order parameter direction has semicolons inside. This is the half, half, half point of a face-centered cubic structure. And around each Bragg peak, there's going to be 8 of these half, half, half peaks around the Bragg peak, right? 8 satellites, 8 superlattice peaks. But only 4 of them are inequivalent. If you take half, 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 and minus half, minus half, minus half, they differ by a reciprocal lattice translation, and so we don't include all of them. We just take 4 of the 8 corners, and those are the representative arms of the star of K. And basically, my spheres here, they represent the intensities of those 4 superlattice peaks. That's my intention. So basically, if you take the A parameter and you adjust, you take that symmetry mode and you drag the slider and make the structure evolve, it's going to take one of those 4 peaks and change the intensity. But if you take the B parameter and adjust that, it's going to adjust one of the other peaks. So you've essentially got 4 waves traveling through the crystal here, and these 4 parameters are going to adjust the amplitudes of those 4 waves. So I haven't forgotten Manu's original question. He just sent me off in a certain direction. And so, of the 3 arms, 1, 2, and 3 of the X point, here are the 3 arms for the X point, A, B, and C. Only one of those 3 waves is non-zero. The other 2 are 0. So in principle, you could have waves traveling in 3 directions. But in this case, right here, here we go. In this case, only one of the 3 arms is non-zero. So there's a close relationship between the order parameters and the diffraction pattern, oft times. So it's important to realize that this is a reciprocal space motivated model, symmetry mode analysis, right? Symmetry modes are waves. So I hope that helps.
At the end of the list, you have the active K vectors. I mean, at each row.
Yes.
And sometimes you have 3 K vectors, and sometimes probably you will have less.
Yeah, this is the R point, the M point, and the X point. And for some of these down at the bottom, the R point only has one representative arm. The M point has 3 representative arms, and the X point also has 3 representative arms, and they're all active. For this bottom case, you see all of the order parameter components are non-zero. So we go in order of increasing complexity. This is the true joint order parameter, and this is an abbreviation. P means 1, C means 2, and S means 3. So with the S here, you can see ABC, you have 3 variables. With the C, you have 2 variables. With the P, you have 1 variable. So this label here is an internal abbreviation for the order parameter direction. All right. That was a great point that I had hoped to talk about anyway, Manu, so thank you. All right, let's go back to the distortion page. So I'm probably going to run out of time here before I get very far. So Juan has often told me that it's a pain to create examples to go through and choose the options one by one. One possibility, is to click subgroup tree, and that will generate a tree with all of the structures that are intermediate between the parent and the child. In this case, there's 29 of them. If you want to simultaneously make models for all of them, you come down and you click these buttons here. We could have a full prof button too. No one's ever asked me for one, but if you want one, I can add a full prof button. And I think it would only take a few hours of effort. And then down at the bottom of the list, sorry, it's slow. There we go. Now you can, for example, open the CIF files and save it to the desktop, or maybe to that same location where we were looking before. And if you open the zip file, you have a CIF file for each, an MCIF file. It's really a magnetic CIF file. It just says CIF. I don't usually put the M there, but you have a CIF file for every model. So for example, if you knew the shape of the supercell, you could invoke a child with space group P1 in the appropriate supercell and generate all the models that fit inside that supercell, and then try them one by one. Might be an easier way to generate the output files. The Bilbao Crystallographic server has a very nice graphical tool, subgroup graph, for visualizing the tree. I use it often. Okay, let's look at another method. Method 4 is very powerful. This is the method you use when you already know the answer and you just want to analyze it. So, for example, if I have a child structure that's published or downloaded from the Bilbao Crystallographic server, there's the published magnetic structure. I think this was a publication from one of your early papers, Juan, this particular structure. I'll give it a second. I don't know why it's taking so long, because I'm the only one on the server. Not sure what my computer's doing here. Okay, so we're going to compare a published parent with a published child with its parent. And when you do this, you have to tell it what's the relationship between the unit cell of the parent and the child. It doesn't know, but it can guess. And it usually guesses quite well unless you have a huge lattice strain, and then you actually have to enter it by hand. But here we'll just accept the default guess. And the origin shift is handled automatically, so we only have to choose the basis. If it doesn't find the origin automatically, then you have to do a little bit of work. But in any case, we've now done a representational analysis of the child relative to the parent, and you can see both the magnetic degrees of freedom and the non-magnetic degrees of freedom are all there. If I go to the modes details page, which is quite nice, it has the parent structure, it has the subgroup details, it has the undistorted child structure before you turn on the symmetry modes, and then it has the distorted structure that has displaced atoms and non-zero magnetic moments. These are each of the relevant modes, R4+, R5+, and it shows you, for each atom, you have the position and also the direction of displacement, or if we're doing magnetic moments, the direction of the magnetic moment for each mode. So X5+, for example, takes the oxygen at 0, 0, half, or the manganese at 0, 0, half in the child, and applies a magnetic moment in the -X direction. So it has all of the mode details. It also has a summary of the mode amplitudes. So for example, you can see how much each IREP contributes. R4+ makes a very big contribution. This is measured it's the root sum squared displacement in the supercell. It's in angstroms. The X5+ is also quite big. M3+ is even larger. And the total root sum squared displacement over all of the modes, all of the contributions simultaneously, it's 1.72 angstroms of displacement aggregate. So the magnetic moments, you can see we have 3 magnetic modes, only one of them is non-zero. You can see the amplitude of that particular mode. And the second column is relative to the parent. So this number is summed across the child supercell. But if you rescale it to the parent cell where there's only one manganese site, you see the magnetic moment on that manganese. Another thing to consider, let's look at you can generate the PCR output. I think Juan showed this very nicely yesterday, so I won't spend a lot of time on it. we'll just open the file. Notepad. So you can see the JBT is -6, and the ISY is 2. Like Juan described yesterday, you have the basis, details about the magnetic space group. You have the atom positions and magnetic moments. And then these are the modes. So these describe the details of each mode, which way the atoms move, which way the magnetic moments point, and these are the mode amplitudes down in this section. I think the SIF output is a little harder to read. It's very useful, but it's a little less intuitive, but it also has some nice features. So for example, here is the child structure, both the magnetic moments and the atomic positions. These are the symmetry modes. You have the full symmetry mode label. Here you have the parents, for each mode there's a name. You have the parent space group, the K vector, the space group IREP, the order parameter direction, the affected atom and its Wyckoff site. It's either displacive or magnetic. It can be either. These are the displacive modes. The magnetic modes are down here. So these are the 3 magnetic ones. You also have the site symmetry of the local atom site, and the amplitudes. Notice here that we have one IREP making multiple contributions. So that IREP can affect the lanthanum, and X5 plus can also affect the oxygen. And so I think it's important to realize generally when you're doing more complicated structures that one IREP can make multiple contributions to the structure. I think that's the end of the tour of the commensurate stuff. After lunch, I'll maybe spend another half an hour walking through some incommensurate examples. So thank you for your attention.
To a question.
How did you get, I didn't catch how you got this last C file?
How did I generate the file?
Yes.
I don't understand that.
I mean, you show first the full prof PCR, and then you show a C file. Just by clicking there, normally if you create a C file, is a normal C file
you can use
without modes and something.
Yeah, the modes are all in the SIF file too.
Oh, okay.
So the Topaz output, has all of the mode information. The SIF file has all of the mode information. If you do a refinement in GSAS, for example, of the structure after you generate the model, you can export the SIF file and import it into GSAS. GSAS, as far as I know, does symmetry mode analysis. It'll read my SIF files, but only non-magnetic ones. I don't think you can bring a traditional magnetic model. You can still export this and import it into GSAS, but GSAS won't use magnetic symmetry modes, only non-magnetic symmetry modes. But the information's there, and also all of the symmetry mode information is in the full prof output.
I would like to make a comment about ISOSIF, your program, that it's very useful to check when you have a problem with a zip file that it's not read by some programs, or it gives some error and you don't know which. I always use ISOSIF, and ISOSIF just gives you which line is making problems. I mean, that's a very useful feature of the ISOSIF, because our programs, when they have a problem with a zip file, they don't just stop.
They just crash, right? They just crash, yeah. Thank you.
How to get a list of subgroups, but you have already selected one order parameter direction. What I would like to have is when you have well before that, when you have to select the combinations of irreducible representations, for instance.
Mm-hmm.
You have a combinatorial problem there, and then you will get the previous dialogue to that, and then what would be interesting is not the subgroups also. Oh, well, that is interesting, of course, but it's just the combination.
One thing that I'll point out, I mean, I understand that. If you drop the symmetry all the way to P1 in a cell large enough to include all of the arms of the star of each of the K vectors that are relevant, all of those combinations will appear somewhere in the list.
Yeah, well,
They will all be there, and you could do just write a little script that goes through and picks out the ones that you like, because for each one you can see which IREPs and which combinations are present. You know.
but it's for a practical point of view. In order to, for example, test
Yes.
the things, you
Yeah.
have to generate the PCR file for all of them.
Yeah.
Then it would be interesting, because in such a case, you can, when you have experimental data, you have the propagation vector, you have the pattern structure, then you have a lot of possibilities. Sometimes there are many possibilities, and then when
Yes.
you have to go one by one, you spend time. And then it is possible, if you have the PCR file or the CIF file, it doesn't matter, all these possibilities without going to lower symmetry.
Yeah.
Just what you get.
So maybe have a button down at the bottom that means do all of them, and generate a zip file with all of the all of the CIF
something
files,
like that.
right?
It would be interesting because, that simplifies probably the life of the experimentalist.
Right. Good suggestion.
This morning section is completed.
Yeah.
Okay. Let's think out of the speaker again. Before lunch, you have something else? 没有什么事吗 ？OK， 没什么事哈。
Okay. 聪明不够，谢谢。Okay, why don't we do a couple of incommensurate examples? And then we'll begin the hands-on part of the tutorial. So I hope you enjoy a couple of incommensurate examples. So in ISODISTORT, I'll just continue working with a perovskite parent. This time I'm going to upload the lanthanum manganite parent from the exercise folder. And the incommensurate option is only available through the method 2, which is the general method. Remember that method 1 is a filtered search over pre-tabulated, very simple cases, one IREP, and only special K vectors at the corners of the Brillouin zone. Method 2 is general. You can combine, you can do commensurate and incommensurate K vectors. You can combine them together. You know, you've got a lot of options. If I want to do something really, really simple, for example, I could take the delta point and I could set the K vector equal to some reasonable value, like 3.127 or something like that. And I could say that I want one modulation. And if I do that, that particular K vector is going to have a couple of IREPs to choose from. In this case, I have only two choices. I'll just pick one of them. This is random real-time exploration. I choose the IREP. And then because the IREP is multidimensional, there will be a couple of different order parameter directions to choose from. This particular IREP is a 12-dimensional IREP. So the matrices that represent the symmetry elements are 12 by 12 matrices. And I'm just going to pick the simplest case here. So I'll choose the first order parameter direction. And the result of this order parameter is a superspace group. It's a magnetic superspace group. And if I want to visualize and see what are the degrees of freedom that are available, I go to ISOVIS. I'm not sure why it's so slow. And I find that I have some degrees of freedom to work with. Exactly one in this case. It appears to be, I did this randomly. I didn't prepare in advance. It appears to be a helical phase, helical magnetic structure. And it's incommensurate. And if you look at the symmetry operations in the CIF file, you can export this CIF file and convert it to PCR format for refinement in full prof. There we go. So you see, here's the basic unit cell. Here's the number and the symbol for the magnetic superspace group. We also have a number and a symbol for the magnetic point group. In this case, the symmetry group is a type 4 magnetic superspace group. And so, as Professor Perez-Mato said earlier, whenever you have a type 4 magnetic space group, the point group is always gray. And so it's a paramagnetic point group. And therefore, for example, it does not support ferromagnetic moment. So here are the symmetry operators. So you have one modulation. It's a fairly simple distortion. We also have some additional, this is an anti-centering operation. You can tell that there's an anti-centering in this group, because when you look up here at the superspace group symbol, you see the 1' from the time reversal group, and it's combined with a 180-degree phase shift. S means 180 degrees. So this it has an anti-translation, and here's the operation right here for the anti-translation. Here are the positions of the atoms in the commensurate cell, and in the basic unit cell. Initially, I didn't assign a magnetic moment, so I haven't activated it yet, and so they're currently all 0. And here are the Fourier wave vectors. So you can see the manganese atom has a wave with an X, a Y, and a Z component. And the free parameters that are allowed by symmetry are the real part of the X component and the imaginary part, the sinus part of the Y component. And so these two end up being 90 degrees out of phase, and you get a spiral. And of course, you can export that. Does anybody have any questions about that? I'm going to just stop for a moment. All right, let's do a more interesting example. That was too simple. So this time I'm going to upload one of the examples from the tutorial. I'm going to open orthorhombic terbium manganite. It's just a distorted perovskite with a root 2 by root 2 by 2 supercell. We can see it here in ISOVIS. I think. Maybe not. Okay. Sorry. I turn off the displacements. I'm only interested in magnetism with this example. And maybe we turn on magnetism for the manganese. So it's as simple as possible. Okay, so now I'm going to superpose two magnetic incommensurate waves. So I'm going to hit 2 here. I'm going to change it. That will rewrite the page. So now I have 2 IREPs. And for both IREPs, I'm going to choose the sigma point. This is the K vector 0, A0. And I'm going to make A 0.27. So both of these modulations have the same K vector. So this is a single K structure. And I'm going to do one incommensurate modulation. It looks like we have a sum of two, but because it's the same K vector, we really only have one independent modulation. And then I choose the IREPs next. So I'm going to choose sigma 3 and sigma 2 as my magnetic IREPs. So I've picked the K vectors and the IREPs now. Now I need a joint order parameter. And there we go. There are only three options. This is the interesting one that is observed in the published structure. These two are monoclinic. This one's actually orthorhombic because of the way the waves couple together. So I'll choose that one. So I'm essentially building a model. So we have a superspace group symmetry with a symmetry group and a basis and an origin. And we have a number of different symmetry modes available. Sigma 3 provides 3 modes. Sigma 2 also provides 3 modes. Gamma 1 plus is the identity IREP. And so it always includes the parameters that were already in the parent structure. So gamma 1 plus governs the degrees of freedom in the parent structure. Let's visualize. So I go to ISOVIS. Thinking. There we go. So here's, I think I can improve this a little bit. Maybe by reducing this number here. This is just the bond lengths. It draws bond lengths. Any connection between two atoms smaller than that distance, it draws a bond. It's kind of annoying. So I'll try again. And we'll take a look at this modulation. It's actually quite an interesting case. Here we go. So let's zoom in a little bit. Turn off the cells. Maybe zoom in. And we see we have a couple of different degrees of freedom. Here's a longitudinal wave. This is a longitudinal modulation. This one is transverse. This one is actually quite interesting. Here we've got something out of the plane in the other direction, like this. What else have we got? So here's another longitudinal wave with a different phase. Another transverse wave. So I'm going to choose this one here for my longitudinal component. And for sigma 2, I'm going to choose this one. And I think together you can see that it forms a cycloid. So I can't make them rotate yet, but the new version of ISOVIS will make the phase rotate, like what you see in the JMOL examples from MAGAN data. So we've essentially combined a longitudinal wave and a transverse wave out of phase. 2 different IREPs combined to give you this cycloidal structure. And it's important to note, and I think I mentioned this on Monday or Tuesday, it was yesterday, that these 2 modulations together break the inversion symmetry for the structure and allow ferroelectric displacements. So, any questions at all about this example? Okay. Let's do another fun example. So this time, I will choose a simple hexagonal lattice as my parent, a single sheet. I'll call it the skyrmion parent. It's only got 1 atom in the unit cell. And I'm going to turn on occupations, displacements, and magnetic order parameters, just for fun. And then this time, I'm going to choose the, let's see, did I hit change? I can't remember. Got to make sure. There we go. So method 2, I'm going to choose the lambda point, and we're going to do an incommensurate wave with a large unit cell. So I'll choose a k-vector of 0.1, 0.10. And this time I'll choose 2 independent modulations instead of 1. And actually, I think I'll even go back a step. And I think I'll superpose 2 irreps in this case. It's more interesting if I do 2. And again, I'll choose them both at the same k-vector. 0.1, 2 modulations, 0.1, 2 modulations. There we go. And I'll superpose 2 irreps. Lambda 2, or lambda 3, and lambda 4. There we go. This should be interesting. Get quite a few different order parameter directions to choose from. There we go. Yeah, and they're long ones, you know. So I think this second case, A0, 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 B0, 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 is very interesting. So I will choose that one. I've already done some exploring, so I have some idea of what cases I want to look at. And I think we're almost there. There we go. Okay, so we have a symmetry mode analysis completed, and now we'll visualize the result. In a minute. There we go. Okay, so here we have a single sheet. In this case, it's intended to be a monolayer of iron. It's a hexagonal lattice. And I'm going to take the lambda 4 parameter and activate it. You don't see anything happening unless you turn the thing perpendicular to the sheet. You can see that you have a mode that is actually out of plane. You know, I think it will be nice if I make the magnetic moments a little bigger. Let me do that. Length of magnetic moment vectors. Let me maybe double that. Actually, I think that was too much. Let me try just doing 1.0. Here we go. So we'll reopen the visualization. There we are. Okay, and when you turn it sideways, you can see you have a modulation, a 2-dimensional modulation of the out-of-plane magnetic moments. If you drag lambda 3, you find a skyrmion lattice. And so we have a series of magnetic vortices wrapping in all in the same direction. So the skyrmions, you know, as Dimitri mentioned, in order to give you full coverage of the sphere in the 3-dimensional order parameter space, have both a vertical component and an in-plane vortex component. And together this gives you the skyrmion structure. Now I added some occupational and displacive degrees of freedom just for fun here. You know, you can do that sort of thing. That mode would be possible. You could also make the occupancies vary in such a fashion. And those are the kinds of degrees of freedom that you can expect to encounter here when you combine these modes together. If you animate all of them together, you get quite a nice visual pattern. So this is the skyrmion lattice. So let me pause this, and I just want to point out that the symmetry group is interesting. If we look at the CIF file and look at the operators, I really don't know why my server is running so slowly. I'm the only one using it. I think my computer must be doing something big in the background. There we go. Okay, so this is the CIF file. So here is the basic unit cell of the hexagonal lattice. And here we have the superspace group number and the symbol. It's a two-dimensional modulation, so you have two incommensurate waves. And actually, in reality, there's three waves, not just two. This I'll demonstrate. When you come down here and look at the list of waves, these are the two fundamental waves. So 0.1, 0.10, that's the first wave. Minus 0.2, 0.10 is the second wave. But there's also a third one. You remember K1 plus K2 plus K3 equals 0 in this case. So you get a third wave running in another direction. Let's take, I'm kind of repeating myself from a past lecture. Let's go back and take a look at that. Sorry, there we go. Let's see, where did I put it? Talks, here we go. Magnetic superspace, that one. Let's go back and look at that. This is the skyrmion lattice here that I just illustrated. And we have a nice picture of the K vectors down here. There it is, right there. So in this case, you have three K vectors that are related to one another by symmetry. And there's this relationship between them. K1 plus K2 plus K3 equals 0. And so they're not independent of each other. This relationship causes K3 to depend on K1 and K2. So it's not linearly independent. And so K1 and K2 give you superspace direction. They give you new superspace dimensions, but K3 does not. And so when you look at the superspace group symbol, right here you see K1 and K2, but K3 is not listed because it's not independent. Here are the symmetry operators. You know, if we didn't know what the group was, you could copy those symmetry operators into the Find SSG tool of the isotropy suite. So this is Find SSG. We click on that, and we copy the operators into position. And we say, what group is this? And, oh, I forgot to turn on magnetism. Made a mistake there. You got to click the magnetic button. There we go. And I believe this should work. It worked yesterday. So it has to do, it's actually quite an intense calculation. But it looked at the table of hundreds of thousands of superspace groups and was able to identify the correct one. 177, 0.2, 0.83, 0.6, 0.153.1. And if we look at what's here, that's exactly the right answer. So it's quite a nice tool. If you're working in IANA and you are doing some exploring and you create a superspace group, you can copy the operators into Find SSG to identify the superspace group. And now I believe IANA actually has a direct connection to the isotropy server. So I think when you develop your model, you can do a direct call to the isotropy suite server and retrieve this information, which is quite a nice feature. Okay, the mode amplitudes here are also interesting. So it turns out you've only got 1 degree of freedom. So the X component of the wave for iron 1, the Y component for 2, and the Y component for 3 are all related. It's just one parameter that's free. And this is all dictated by the magnetic superspace group. Okay. Any questions about that? Sure. Sorry, yeah, I meant to do that. I apologize. I think I showed the displacive one. Let's look at that again. So we open the CIF. Takes just a few seconds to generate it. I have a lot of security code on my server. So I think it doesn't trust me, and it's checking everything I do to make sure there's no viruses. I think that's what's taking so long. Here we go. So here are the displacive parameters. These ones are for the magnetic moments. Thank you for requiring me to do that. Any questions? So when you say which components go with which K vector? Yes, yeah, definitely. So this number here, 1, 2, and 3 are the K vectors. Could you use the microphone? Yeah, my ears are really terrible.
Sorry, I lost for you for the result with what you try to show us with the skirmion, but I try also to use ISODISTORT and methods too. I need to first use some propagation vector components for AA0 order per vector, or order parameter vector.
You want to know
yeah, which
components of the wave vector?
Oh, the components of the wave vector.
Yeah.
It's right up, let's see, where is it? Fourier parameters. It's right here. So this is K1, K2, sorry, K2 and K3.
But
Is that helpful?
But you introduce a single wave vector. You introduce a single wave vector, then it's the program that generates the other ones, no?
Yes, the program generates the others. That's it. That's exactly right. If we go back to the search page here, you'll remember I just specified AA0, and then on the order parameter direction, I chose a particular case where here are the active K vectors. So they were chosen at the time that I selected the order parameter direction. Remember that the order parameter direction has semicolons that separate the K vectors. And so this part is from K1, this is from K2, and this is from K3. Observe that all of them are non-zero. K1, K2, and K3 each have a non-zero parameter, A, inside. And it's important that A, and A, they're all equal. So there's just 1 degree of freedom. If you come down to this order parameter down here, you see A, B, C, D, E, F, G, H. In this case, you've only got 2 active K vectors, and both of them have 2 degrees of freedom in the structural modes that they provide.
Branton, can you show what you get when instead of putting 2 modulations, a single modulation? Because the list is going
Instead of 2, just do 1?
down, yes, just to show what's
Yeah,
the difference.
I apologize that I don't completely understand your question, but the way I interpret it, here I'm just doing 1 mode instead of 2. Is that not what you mean?
At the beginning, when you choose the wave vector for the 2 reps, you put 2 incommensurate.
Oh, okay. 2 superspace dimensions. Yeah. Yeah, that's an excellent point. Excellent point. So I'll go back and do exactly that. So let me close these pages, and I'll go forward to the order parameter direction. Oh, wait, no, actually, let's do it right here. Let's just do 1. Actually, why don't I simplify things and just do 1 IRAP now? It'll be a better illustration. So we'll do...
You can do the same thing with 1 modulation, no? That's
So here we do 0.1, and choose one modulation. This time we're only looking for 3 plus 1 dimensional superspace group examples. Gamma, sorry. My bad. Okay. The gamma point has no degrees of freedom. Okay, so here we have a couple of magnetic irreps. I'll choose lambda 3 again.
But you can do it also with 2 irreps, not only a single one.
You could, yeah. Yeah. So in this case, we're going to get a very different selection. Yeah, so you can see the options are very different in this case. Now you only have one active K vector, so you just have a modulation wave in one direction instead of having 3 waves simultaneously. So I think there's one other case that I would show you, but I'll let you explore it on your own. It's the dysprosium manganese germanium case. I'll just pull in the result because I've already done the exercise myself, and I have the result, and I saved the result. And so I'm simply going to import it just to show you what it looks like. Exercise is completed. So this is dysprosium manganese germanium 6. So it's a 1-6-6 phase. Yeah, even importing it takes a few seconds. There we go. Okay, let's visualize the result. So this is one of the examples that you can create by hand. It's a model that you can create. This waiting was far more painful than I thought it would be. Okay, there we go. So one of your exercises is to superpose 2 magnetic irreps, a commensurate irrep and an incommensurate irrep, in order to achieve this model, and then export it to a CIF file. All right. At this point, I'm going to do something maybe that you don't expect. I don't know. We'll see. I'm gonna try to surprise you. So we have too many people here to all access the server at once. I think we would crash the server if you were all submitting jobs at the same time. So we're going to break up into teams of 2 people each. So if you're 2 people and you're sitting next to each other, one of you will open the isotropy suite, and the other will open the instructions. So here's the instruction file. It was in the download. So one of you can follow the instructions of each exercise step by step on your laptop, and your partner will have the isotropy suite on his laptop. Also, I think still we have too many, and so I've created 2 servers instead of 1 for the workshop. So let's see here. There we go. So I think on the left side of the room, your left, this side over here, you're going to use the iso.byu.edu website. And if you're on your right side, we'll divide it right down the middle, right here. If you're on the right side, you're going to use a different address. Landau.b.byu. It's an alternative. It's the new server instead of the old one. What's that? I thought I heard a question. Okay. Now, what I want you to do, you can use any browser you want. I like Firefox, but you can use your favorite browser. And you're going to work through the tutorial exercises at your own pace. You can switch partners if you want to. If you have someone that works on a similar problem as you and you want to change seats, that's totally fine. You can do that now, you know. But I'm going to have you work through the exercises together as teams, and I'm going to walk around the room and answer questions. if you have any. If you have a question, raise your hand. If you're a beginner, if you have no experience with the isotropy suite, I recommend starting with the first exercise at the beginning, exercise 1. But if you're an experienced user, you're welcome to use your own research problem, and I'll come around and answer questions as best I can. My only request is that you please try to do simple things. If you do something really complicated, you can make the server, load the server down heavily. So try to do light and easy things instead of super complicated stuff, okay? Like please don't try to superpose 8 magnetic ear apps. That would definitely bring the server down. So, okay. Thank you. So yeah, get started. If you don't make some noise, you're not doing it right. So I'm expecting this to be a noisy experience. So please start talking. In the tutorial file set, there's a folder called Visualizations. If you click on that, you have a bunch of examples, and you can take each one and open it and explore it. So I recommend, if you don't have any experience at all, maybe take a look at these examples and just open and explore them visually. It's up to you. Thank you. Continue.